Welcome. So now we're going to go over transformations. And the rules for transforming exponential growth and decay graphs are exactly the same as the transformations for every other graph we've done. The format for, I'm going to have an arrow here so I can point. Oops, come on. The format for exponential equations is y equals ab to the x minus c. And I should preface that the format for exponential equations with a horizontal translation only. So we're going to look at each of the translations separately. So this would be a horizontal translation if we add or subtract something to x. A is the starting value, b is the base, x minus c shifts the exponential function to the right, x plus c shifts the exponential function to the left. This a, the starting value, is also a vertical stretch or compression. Depending on if it's greater than 1, it'd be a stretch. If it's between 0 and 1, it's a compression. All right, so horizontal translations. If you have x plus c, the graph shifts to the left. X minus c, the graph shifts to the right. The blue graph here is y equals 2 to the x. The red graph is y equals 2 to the x plus 3. Notice that it is shifted, all the points are shifted 3 units to the left. So instead of a point 0, 1, because the starting value is 1, we have a point negative 3, 1. Right? The x is 3 less. Instead of a point 2, 4, we have a point negative 1, 4. 3 less on the x. And instead of a point 3, 8, we have a point 0, 8. So all of the points are just shifted 3 to the left. And then if we have x, we have b to the x minus c, that is to the right. So the green graph is shifted, somewhere is this, oh, there's the equation. I know it's there somewhere. The green graph is shifted 4 units to the right. So again, instead of 0, 1, we have a point 4, 1. Instead of 2, 4, we have a point 6, 4. And instead of 3, 8, we have a point 7, 8. All the x values have moved 4 to the right, while the y values have stayed exactly the same. So again, if you have x minus c, it is to the right. X plus c is to the left. Right? It does not change. Nothing changes the domain. The domain for all exponential functions is negative infinity to infinity. The range will now be 0 to infinity. And moving along, vertical translation. So vertical translations are caused by adding something to the whole function. If it's positive, it shifts up. If it's negative, it shifts down. Vertical shifts change the horizontal asymptote of an exponential function from y equals 0 to y equals whatever the value is that you added to the function. So now adding to our, come on, little arrow, adding to our format for exponential equations, the plus d, right, would be a vertical shift. If that plus d is, we're adding a positive value, the graph will shift d units up, and so will the horizontal asymptote. If it's a negative value, the graph will shift d units down, and so will the horizontal asymptote. Right? So if here we put a C, but on this chart here there's a C, but just to distinguish between horizontal and vertical when there's both, I have a D, and usually it is shown as a D. Right? So but whatever's added to the exponential equation not added to x, but added to the whole function, shifts it vertically up and down. So let's take a look at a couple of equations. The blue graph is still y equals 2 to the x. The green graph is y equals 2 to the x minus 4. All right, so the horizontal asymptote is shifted 4 down. And I just chose one point to highlight. So instead of a point 0, 1, we have a point 0, negative 3. And the range has changed from 0 to infinity to negative 4 to infinity. The red graph is y equals 2 to the x plus 3. And by the way, that vertical shift could be in front rather than at the end. So that first graph could have also been y equals negative 4 plus 2 to the x. The red graph could be y equals 2 to the x plus 3, or y equals 3 plus 2 to the x. Instead of a point 0, 1 now, because the graph has been shifted up 3, we have a point 0, 4. And the horizontal asymptote has changed to y equals 3 because we've added 3 to the whole function. I'm just going to move that arrow. All right, so we've got horizontal translations and vertical translations. Did the graph? Oh, there we go. Reflections. All right, so if there is a negative in front of the base, it's going to reflect the graph about the x-axis. All the y values are now going to be negative. If the negative is on the exponent, it reflects the graph about the y-axis, and actually it just changes it to exponential decay. So we could simplify y equals b to the negative x and just make it y equals 1 over b to the x. Right? And then you don't have to worry about a reflection. It's probably easiest to just simplify negatives on the exponent to make the base the reciprocal. All right, so here we have y equals 2 to the x. All right, the red graph is y equals negative 2 to the x. All right, all the y values are now the opposite, and the range changes to negative infinity to 0. Right? In this case, the starting value is negative 1. If the negative is on the exponent, we do have a reflection over the y-axis. So this green graph here is y equals 2 to the negative x, but we could just simplify that to y equals 1/2 to the x, which we saw in the last Nearpod, right? The exact same equation, right? So this is really exponential decay. And it's a good idea to actually simplify it so it stands out as being exponential decay and you don't think it's growth, because it's not. All right, nothing about the horizontal asymptote changes, right? Just the y values become negative. If the negative's in front, it changes from growth to decay, or decay to growth if the negative is on the exponent. Horizontal stretching or shrinking, right? So vertical stretching or shrinking is the a value, and we just multiply the y values by that. Horizontal stretching or shrinking affects the graph by the reciprocal. All right, so the blue graph there is y equals 2 to the x again. The red graph is y equals 2 to the 1/2 x. With that 1/2 as a coefficient on the exponent, the x values are going to be have to be twice as large to get to the same y value. So that has the effect of stretching the graph horizontally It makes the graph wider. So the graph is going to be horizontally stretched if the coefficient on x, sometimes it's called b, although my little chart here really likes c. But if that coefficient on x is between 0 and 1, the graph gets horizontally wider. We're going to multiply the x values by the reciprocal. It's kind of similar to when we were graphing trig functions and we had a change in period. Right? The x values actually changed by 1 over b. If that coefficient on the exponent is greater than 1, it's going to shrink the graph horizontally. The graph will be skinnier. So the green graph here is y equals 2 to the 4x. So with the 4 in front, I need a value that's 1/4 as much to get to the same y value. All right? So if I did a couple examples here, if x is 2, right, for the blue graph, I would have 2 squared or 4. For the red graph, I'd have 1/2 times 2, which is 1. 2 to the first power is 2. But for the green graph, 4 times 2 would be 8, and 2 to the 8th power is 256. So that coefficient really dramatically affects the x values by needing a much smaller x value to get to the same y value. And moving along. So here are all of the transformations summed up here and all of their effects. I think this is in your notes, and I think I have all the information in there, but if there's something missing, add it in. So vertical translations, you add or, actually, and I'm going to get rid of this part here. Just ignore that part. Boop. Let's go through this. So vertical translations, you add or subtract the value to the function. It changes the horizontal asymptote, it affects the range, and you simply add or subtract to y. The horizontal translations, you add or subtract the value to, is something added or subtracted to x. If it is x plus, then it is a shift to the left and you subtract from x. If it is x minus c, the graph is shifted to the right and you add to the x values. Vertical and horizontal stretching. Actually, I'm going to get rid of this. We're going to I want to actually practice us not treating them as a base graph, but dealing with each transformation separately. Now that you've done trig functions, I think you can certainly handle that, and it will prepare you more for pre-calc. So a vertical stretch, just if you have a coefficient in front of your base, it stretches it'll stretch the y by c. So this one is y. And you would just multiply by c, right? If it is a coefficient on the x, it's going to affect the x by 1 over c. And so for vertical, you multiply by whatever the value is. And if it's horizontal, you multiply by the x value. Reflections, the negative so we have what happens if it's and you can get rid of this too, because we're going to treat them separately. If those are in your notes already, don't worry about it. Or you can cross them off. Reflections, if it's on the in front of the base, then it's going to be a reflection about the x-axis. It'll affect the range. If it is on the exponent, we're going to rewrite that as the reciprocal because it's really decay, right? So instead of keeping it with the negative, we'll change the base and then we'll treat it as decay. Unless, of course, the base is already between 0 and 1, and then it would change to growth. But we'll deal with the reflections on the negatives on the x by rewriting. But everything else we'll deal with by changing the x and y values. So the stretching has to occur before translations. So, and the same thing with reflections. So this is first, and this is done second. All right, so you do have to deal with any stretching or reflecting, any dilations before translations. So if that's not in your notes, do add that the stretching and reflections are first and the translations are second. All right, and this just kind of sums them all up. All right, so f of x equals ab to the x minus h plus k. We could have a coefficient in front of the x as well. So now we'd have f of x equals ab to the raised to the c times x minus h plus k. H and k you're probably more familiar with because that was the same letters for the horizontal and vertical translations for quadratic functions. Right? There's nothing really special about the letters except some letters just get used more than others. It's their position. Right? So if it's added or subtracted to x, moves it right and left, right? Because x is horizontal. It's already understood that there's always a negative with the x minus h. So if you see a plus, it's really x minus a negative, and it's going to move to the left. Whatever the sign of the value you add to or subtract to the whole function is the vertical translation. It's up if it's positive, it's down if it's negative, right? And then if the starting value is negative, the graph is reflected. If there's a negative on x, the base is really the reciprocal, right? I don't need this part because we're going to treat the base. Our base graph from here on in is going to just be this. Y equals b to the x. Everything else we're going to treat as a translation. Right? That'll get you used to the effects of different values on the base graph. Right? And that's all of our main values. And then the coefficient in front of x, if it's greater than 1, horizontal shrink, as we saw with the graph of f of x equals 2 to the 4x. And if it's between 0 and 1, horizontal stretch, as we saw with the graph of f of x equals 2 to the 1/2 x. And I think I'm gonna, I'll go over these steps, and no, you know what? I'm going to pause it here, and I'm going to do the rest on the next video. So thanks for watching, and bye for now.